All right, let's talk tensegrity. You might have seen those wild sculptures where bars seem to float, no glue, no bolts, just magic. But trust me, it's not magic, it's tensegrity, a structural design principle that's all about balance. Tensegrity, short for tensional integrity, is a system where isolated compression elements, think rigid rods or bars, never touch each other. Instead, they're held in place by a continuous network of tension elements, usually cables or strings. The bars push outward, trying to escape, while the cables pull inward, keeping everything locked in a delicate dance. This whole idea was formalized by Buckminster Fuller in the 20th century, though Kenneth Snelson's sculptures made it real for the world to see. Imagine a structure that's lightweight, flexible, and crazy strong for its size. That's tensegrity in action. Let's break down the core principles. First, continuous tension, discontinuous compression. All the cables connect, forming a network that pulls everything together, while the rods never actually meet. Second, pre-stress. These cables are under tension even when there's no extra load. That pre-stress is what makes the whole structure self-supporting. Third, minimal materials, maximal strength. Because tensegrity distributes loads so efficiently, you get a structure that's both light and tough. What makes tensegrity structures stand out? They're lightweight, using just enough material to do the job. They're flexible and resilient, so if you poke or prod them, they absorb shocks and bounce right back. Once you've put them together and tensioned everything just right, they're self-stabilizing, no need for extra supports. They're modular and scalable, so you can build small or go huge. And honestly, they look awesome, almost like they're defying gravity. So where do we see tensegrity in the real world? In art and architecture, Snelson's Needle Tower is a classic example. Some modern roofs and pavilions lean on tensegrity for their striking looks and stability. In biology, your own body is basically a tensegrity system. Your bones act like struts, and your muscles and fascia are the tension elements holding everything together. Even at the cellular level, cytoskeletons use tensegrity principles for support. Engineering and robotics? NASA's working on tensegrity robots for planetary exploration. Imagine a structure that can fold up, survive a crash landing, then crawl across alien terrain. There are also deployable shelters, antennas and more, all built around tensegrity. And hey, even furniture designers are getting in on the action, making tables and chairs that seem to float in mid-air. Let's visualize this for a second. Picture a bunch of rods, floating, not touching, but perfectly held in place by strings pulling from all directions. The rods try to push outward, the cables pull inward, and the whole thing balances itself. That's tensegrity. Forces distributed so cleverly that the system holds itself together. On the math and physics side, tensegrity relies on statics and mechanics. At every node, the points where cables or rods meet, the forces must add up to zero. The way you arrange the parts matters as much as their lengths. And these systems often show non-linear behavior, which means they can adapt and stay strong under changing loads. Why go for tensegrity? You get high strength-to-weight ratios, resistance to impacts and vibrations, scalability, and those visually stunning open frameworks. But there are some downsides. Designing and analyzing tensegrity takes some serious brainpower. You need precision when building, and the way forces move through the system can get complicated fast. Bottom line, tensegrity is a game changer. It fuses engineering, biology, and art into one concept. By mastering the balance between tension and compression, we can build structures that are stronger, lighter, and more versatile than ever. From skyscrapers to your own body, tensegrity is everywhere, and understanding it opens up a world of possibilities in science and engineering.